Hello, everyone. Good morning, good afternoon, good evening, depending on where you are. So, thank you for joining us in this another exciting talk from the CASS talks from the CASS Rio Grande do Sul chapter in Brazil. So, the talk today is by Theocharides from University of Cyprus in Cyprus. He's going to talk about bioinspired joint hardware and algorithm acceleration for edge computer vision. So that's our next event. So let's start the talk today by Theo. Uh, Theo Theocharides is an associate professor in the Department of Electrical and Computer Engineering and the research director of the CAIOS Research and Innovation Center of Excellence at the University of Cyprus. So he received his PhD from Penn State University in the areas of low power and computer architectures and reliable system design, with emphasis in computer vision and computational intelligence applications. So he got several awards and has a lot of experience in the field. And I'm not going to be all the bio because we want to listen from what Theo wants to um, tell us today. So thanks Theo for accepting our invitation from the chapter. It's our honor to receive you here for this very nice talk, and the floor is yours to start.
Thank you very much, Claudio. I am also deeply honored by the invitation, and I'm very happy to be able to share the things that we do in hardware and algorithm acceleration for edge computer vision applications. First, let me make sure that you guys can all hear me okay, and of course, you can see my screen. So before I talk about the topic, though, let me just give you a little bit of a background about our research center, which is called GEOS. GEOS is not an acronym for anything. Instead, it's named after the Greek titan of intelligence, because what we do, we work on how to make systems more intelligent in terms of being able to take decisions in real time for support and data analytics, similar to the way the human body works, where we sense with our senses, we analyze with our brain, we decide and we react with our muscles as the human actuators. So my talk consists essentially of 3 parts. First, I'm going to try to argue why vision is what we call today AI, and why vision at the edge is basically AI at the edge, as it's very well known. Then the second part focuses on how we do want to reduce the data that we process so that our circuits and systems running vision at the edge are more efficient, less power hungry, and process less data. And the third part of my talk focuses on how we can make the actual intelligence, let's say, engines more efficient by inspired by biology and by human perception. So let me go a few decades back. In 1964, actually, Stanley Kubrick, who was a very famous movie director and one of the top science fiction movie directors of all time, produced a lot of movies, among them one of the black humor comedies of that time, particularly Dr. Strangelove, or How I Learned to Live and Love the Atomic Bomb. And what he envisioned, it's in one situation room, or a control room, as a war room, as it was known in the movie. You could see that there is real-time data, there is real-time visual data, coordinates, satellite feeds to inform the people that take strategic decisions about what should happen. And this, of course, came before the ARPANET, before the internet of today, and before Minsky's and Pavert's vision project that started in 1966 at MIT. The question, though, is why is today vision and intelligent edge devices, as we call them, that they see things, become critical? Well, now intelligent systems are everywhere, in traffic, in automobiles, in transportation systems, healthcare, industry, etc. And most importantly, in the areas which we call critical infrastructure systems that compose our modern society and facilitate our ways of life. So if something fails, we need to be able to react in real time, fix it, and hopefully continue seamlessly to provide all these services and facilities to the society. And these systems are evident everywhere in our community. Let that be in the parks that we attend, in the seas, in the forests, in the factories, the buildings, and pretty much everywhere. So we are also familiar with how complex these systems tend to get. The complexity of these systems is, of course, exponential. They produce huge amounts of data, which means that we need to process and analyze this data as fast as we can. And with the increased number of these devices, we are all familiar how this problem becomes critical to address. And the key challenge, which is what I started talking about, what we do at the center, is how to do that in a resource-constrained environment, in a real-time environment, and of course, in a robust, reliable, and secure way to enable these IoT systems, these edge devices, to sense, analyze, decide, and react. So if we go maybe 100 years ago, sensors, or the way we see things, our eyes, essentially, in the human body or mammalian body, are the cameras. And it's not that long ago that people also wanted to memorize, capture, let's say, the moments that humans were able to see. The photo of the mammoth camera of George Lawrence, which dates back to 1900, it's one of the famous pictures of science advancements of the 20th and 19th century. But for those of us who have seen the movie Back to the Future, which was filmed in 1985, we saw that that camera was able to be on the shoulders of Marty McFly, which holds it, as you see from the photo, while he's filming Dr. Brown's experiment with time travel in the well-known movie. Well, if the time travel was actually realistic in 1985, and they were able to travel in 2015, which was then today's future, back then's future, I mean, they wouldn't find hoverboards, they wouldn't find flying cars, but they could find cameras that could fit in our fingers and capture images in extremely high resolution with too much detail and with really good power consumption. So the role of these sensors, the role of these devices that capture information accurately and in real time has played a huge importance into this, what we call edge intelligence or computing at the sensor, as it's mostly known. And the sensors are thankfully abundant in our time. And not only that, they're also very cheap in the sense that we can buy them, integrate them on any embedded microcontroller, embedded device, and do whatever we want with the device, feeding what the sensors capture into our system. Another important aspect is the fact that those sensors are also mobile. They are also of extreme technological advance in the sense that they can capture things that the human senses cannot capture. And they are also remote. They can be placed on remotely operated systems. They can be made to fly, for example, in drones. They can provide data that the human eye or the mammalian vision does not capture, such as thermal or multispectral images. And even if we think about it, we have put such sensors on rovers that are searching to study the red planet Mars. And if you are familiar with the Curiosity rover, you can see a lot of the visual sensors on the photo on the top right of the screen. But of course, the sensors need a brain. Claudius earlier put a picture of Iguazu, and if I'm there and I'm looking and touching and feeling and hearing the waterfalls and stuff, if I don't have a brain, I'm not going to be able to identify where I am, which means probably unequal to false, but the brain takes it a step further and puts it into useful context, which could be, for example, to tell me where I am in the world. I mean, I am in Brazil, and so on. So this is what's really vision. Vision is also, for those of you who are familiar with one of the most popular series of the Game of Thrones specifically, it's what we usually remember as humans. It's our memories. What we see things, and it's ironic because the person that actually says that in the movie is actually blind. What we see things, it's things that we capture, and our memories maintain those visual things and relate it whenever we want to remember something, and so on. And let me share a couple of very interesting facts. When we open our eyes, approximately 2/3 of our brain electrical activity happens, and our 50% of our neural tissue, it's directly or indirectly related to vision. Furthermore, as we evolve as humans, our olfactory cortex, which is essentially our smell processing ability, it's losing ground to the visual cortex. Or if I were to put it in plain words, our vision is eating our smell. And a very nice example is when we go to a restaurant and they bring us a very nicely presented dish. Living in the Instagram or social media world, we tend to take a picture of what we're about to eat before we actually eat it. So that should give you an understanding on why this particular sense of the five senses of the human body is very important. This was also recognized by a couple of AI pioneers back in 1966, more particularly Papert and Seymour Papert and Marvin Minsky, who decided to attach a camera to a computer and try to program the computer to analyze what it sees. And of course, a very nice article in Popular Science back in 2014 comes and explains that vision is not the sensing itself, the sensor, the image. Instead, it's the brain activity that takes place behind the picture. And most importantly, if we put enough processing power, which relates to what we do as circuits and systems, let's say researchers and engineers, it's the circuits and the systems that implement this brain activity. And if I were to go a few decades later, deep learning, which is today's probably most talked about AI area, is inspired by vision, because primarily the way our visual cortex operates relates to the deep neural networks, the types of activities that happen inside our brain, the relationships between features that exist in images, and so on. And I also want to argue that vision was, in fact, the leading, let's call it, area of how AI came out of the AI winter, as it was described before, the early 1980s, and particularly with the advent of multi-layer perceptron that came out in 1986 by Hinton and his colleagues back then. And it was also took off in the early 2000s by, which I'm pretty sure you're all familiar, the convolutional neural networks that were initially proposed by Yann LeCun, and of course what powers today's deep learning approaches, the features that we're able to recognize, put the relationship and associations together, and classify what we see, for example, is a cat or a dog, and put it into context, and so on. This huge demand for applications led, of course, the way to develop these systems in a portable and embedded way, such as Movidius Neural Compute Strip, which is now part of Intel, and of course the architectures that the design, automation, and production companies such as Intel, NVIDIA, and so on are now building to emulate the brain computation. The question that I want to pose today to us is, how do we move, though, from these powerful computing platforms from the cloud, let's call it, to the edge, where we have a lot of constraints and a lot of things that does not allow us to see and process these things in the way that we used to do that right now in the cloud. Cloud computing and edge computing, in our case, obviously differ And if I go back to the cloud computing first, obviously we have more resources. That implies that our models are usually more accurate in the sense that we can analyze better and see better and clarify better the scene, if I can use the word. And of course, the only boundary we have is the budget and of course the needs of the application. However, it can be potentially less secure because when we transmit data from the device that we do the processing to the cloud and back, the sensing, I mean, to the cloud and back, there could be a communication lag. Somebody could steal that data. And of course, the robustness is vulnerable due to various refresh rates and many, many more issues that are characterized by the data transmission barriers that exist by doing things on the device versus sending them to the cloud. On the other hand, if we are able to do the processing on the board, on the sensor, on the edge, then we can do it in real time. We can do it more secure and, of course, more robust. However, we are bound by the constraints, which, as we all know, are very tight on a tiny device, on a small device that operates on power budgets and, of course, limited resources. So how do we make the edge to see? Well, this is not something that started the last few years. Instead, it has something that has been going on for a while, evident by the advancements in both hardware and systems, as well as the open source tools and data and initiatives that take place the last 20 or so years, such as open computer visions libraries that are geared towards very small microcontrollers and edge devices. And of course, the applications that allows us to, that drives these demands, that gives value to these advancements, which are basically found everywhere from industry to surveillance, to mobile systems such as our mobile phones and cameras, automotive, biomedical, and many, many more. This also has spurred a huge ecosystem, companies, universities that work around these areas. Of course, I'm not going to go into who is who and provide it. I'm just making the case that this is a very, very popular topic and very popular area that attracts a lot of attention due to the usefulness in society and so on. And of course, the big names, we're not going to be away from here. We have Google, NVIDIA, Xilinx, Intel, Qualcomm, and many, many more giants of IBM, for example, with the True North chip of AI that are basically racing to build these architectures. And we have already seen in, for example, voice recognition on mobile phones that these architectures can operate and work while running exclusively on the device without the need of communicating the data that has to be analyzed, that has to be processed on the device back to some cloud server for faster computation and back to the device for the results. Jetson Tx2, for example, that is designed by NVIDIA. You can see some prototypes right there to show you how small they are. And Google TPU, Edge TPU as it's called, are two very well-known architectures that address these things at the edge. Tegra X2 is also integrated into a very popular video game console, specifically Nintendo Switch. But it's not only for entertainment purposes. Instead, it has its own applications in computer vision. So the challenge of just taking these huge, high energy consuming devices and putting them on our mobile devices, the sensors essentially, it's obviously quite hard and very, very, very demanding. So what I will talk about in the next 45 minutes or so is how we try to approach this problem and so on. Before I get there, just to give you an idea of what we mean in real life. So if I'm piloting a drone, if I had to do it in the cloud, it implies that I have unlimited resources, pilots, screens, etc., where I get this information and I analyze it as you can see in the picture. I can have an intermediate station which will receive the information, do some processing, send it back, and so on. Or I can just have the tiny processor running on these particular drones, for example, where it orchestrates with the rest of the system to form a truly multi-agent system that collaborate with each other to perform a very nice visual, as you can see on the picture on the right from the Seoul Winter Olympics of 2020. So why does it matter? Well, because in the past, we used to basically rely on some server to do our intelligent processing, but now we can send off the device and let it on its own, give it more autonomy, move the decisions where they need to be taken place, and assist our society. Obviously, we cannot rely on technology scaling only. Yeah, we can shrink a lot of processing power and power and everything that happened in the last 50, 60, 70 years from a room-sized computer to a finger-sized computer, but we cannot just shrink everything and put it on a tiny sensor and call it a day, as we are all very well aware. What we want to do is we want to identify what are the challenges and opportunities of doing so, and in identifying that, then we can choose our battles and try to do that as best as we can. So why do we need to shift this computation towards the edge? Well, as I mentioned earlier, we want to improve our time to action and reduce the latency. Privacy, security, and cost obviously are prime parameters, but we have to outdo the challenges in terms of the limited compute resources that exist on the edge, memory, and of course the storage that comes with tiny sensors and tiny devices and so on. There is also a need to optimizing the models and the structures based on the hardware of choice, whether that will be an embedded platform, a GPU, a CPU, or a custom ASIC or an FPGA, let's call it prototyping. And of course, the algorithms, the tasks that we're trying to do, whether that be, for example, recognizing a pattern, classifying an image as a cat or a dog, for example, and many, many more. And we need to take all these parameters into one complete picture to be able to do that. So to do that, we also have to take into consideration that vision, which is also AI, needs a lot of an insane amount of compute memory and electricity to work, and we all know that. For example, ResNet needs around 30 billion operations. Google's voice recognition needs around 19 billion operations, and many, many, many more. Huge amounts of memory, data, etc., that needs to be processed. So we need to find more intelligent ways, if I can take the irony in using the term intelligent, in doing that. Obviously, this is, again, not something that has been recently only done. Custom hardware architectures accelerating these techniques have been around for a while. Some of our earlier work, actually, that along with one of my colleagues did in the past, was to develop systolic array-based architectures that focus on detecting faces, detecting objects, and in a very fast and low-power way. And of course, where the ability to do that in high-resolution images, which is something that I haven't talked yet, but if we're talking about doing visual analytics using today's sensing technology that comes into extremely high-resolution images, and we want to take advantage of these high-resolution images, then of course we need to change the way we design the systems, so that way we can address the ever-growing challenges of these systems and how it translates back into the hardware demands and the sensor demands and many, many more. So our earlier work actually was able to operate on 800 by 600 resolution images, process around 40 frames per second, which is more than real time, and with over 90% of accuracy. But I'm not going to talk about this right now. Instead, I'm going to talk about how we can think outside the box to address these issues, and how we can rely on bioinspired methods versus computational, let's call them, methods to do things. Especially in the last few years, where there's a lot of work done on the complexity of neural networks to put them on the edge, for example, on NVIDIA Jetson, in the second column of the table that you see in the bottom half of the slide. A couple of very well-known networks, the fast YOLO and the YOLO V2 and so on, they can achieve anywhere between 17 to 5 frames per second, which is not bad, but it's definitely not good if we're talking about applications that the demand for seeing things, fast-moving things, it's more necessary than seeing things as correctly as possible and so on. On the other hand, if we just take a very high-performing neural network such as ResNet, ResNet consists of more than 150 layers, 11 point plus giga multiply cumulative operations per second, and over 60 million of weights, which translates to huge amounts of RAM data, ROM data, huge amounts of data transfer between the network itself, and huge amounts of data transfer between the network. By network, I mean the neural network, and the sensors, the input image, the memory that transfers the image, and so on. So what are the challenges? If we need real-time operation, especially in critical infrastructure monitoring, where we need to be able to decide in a fast, real-time, reliable, and secure way, then maybe we need to design dedicated hardware. At the same time, we're talking about accuracy trade-offs. So do I need to detect everything? Can I trade off some accuracy with some performance? These are all things that can enable us to design more hardware-friendly solution and so on. At the same time, though, we are constrained by technology. So we have a limited number of memory. After all, we cannot stack memory on the chip, or at least not in single layer chips yet. The data flow from the chip outside to the outside world, or to the sensor, or to the video capture, let's say, device, it's a challenge that has not yet been considered when we're designing ASCII circuits for vision. Just to give you an example, an HD frame consists of 32 pixels by 1920 by 1080, which is around 2.5 gigabytes of data that needs to be transferred every second into the vision chip for parallel processing and so on. Obviously, we have to deal with edge-related constraints, power, cooling, battery, cost, and so on. And the way to do that, and I want to argue about it, is that we need to be inspired by our brain. Our brains are extremely important, extremely efficient in terms of how they process data, in terms of the power consumption that they do, and in terms of their robustness and reliability and security and so on. If I go a little bit in the last 20, 30 years or so, we are always trying to see if we can outperform our brains. And this has been running in chess, for example, going back to the Deep Blue with Garry Kasparov games back in 1996, for those of you old enough to remember. But we also have much more recent examples. Back in 2011, IBM Watson was taking into a game of Jeopardy Ken Jennings and Brad Rutter, who were one of very popular players of Jeopardy back then. And most recently, which I hope and I'm hopeful that most of you remember, Lee Sedol, one of the world's top players, versus AlphaGo by Google in the Chinese game of Go. And if I recall correctly, AlphaGo beat Lee Sedol with a total score of 4-1. So we can see that in terms of pure brain processing, we are reaching a point. However, to do that, compared to the human brain that consumes around 15, 20 watts of power every whatever computation, we need 12,000 kilowatts of power, 1 megawatt of power versus 20 watts of the human brain. So our brains are always on. Our brains have an extreme ability to learn, identify, unsupervised, and understand things even from the day we're born. And our brains can allow us to have a glass of wine or a couple of beers and lose some neurons along the way without losing our ability to think correctly and produce, do correct work or intelligent work in our everyday activities. So going back now to vision, there are some opportunities that stem from the application. For example, an autonomous car. I don't need to see if the person is a male, female, child, etc. I need to be able to identify whether there's a person that has jumped into the front of the car and stopped the car. Silhouette-based processing, for example, could do it. If I'm trying to count cars in a parking lot, which is a less critical, let's say, application, I can probably do it in a lower resolution, trade off some accuracy, for example, for performance, and vice versa. So there are a lot of opportunities. And with that, having said that, I'm going to now shift into the part where I'm going to talk about, let's focus on what it really matters for us to process, to see. To do that, let me use as a case study the problem of object detection. Object detection essentially tries essentially to locate a particular object within an image. So if we're looking to find a face in an image, as an example with the well-known image of Lena, then we want to take that particular piece of image data and train a machine learning-based classifier such as a neural network to identify that image. Now, the larger the data, the amount of data in terms of its pure dimension values, like the width and the height and the pixel, for example, number of pixel bits, etc., that I need to feed into my classifier, obviously by far the more complex the classifier will be. So traditionally, when this effort first started, we kept the data that the classifier would see as small as possible. However, if we were looking to look at an image of, let's say, a size 320 by 240, similar to the friend's picture that we see in the bottom left, in order for us to do that, we have to figure out the size of the classifier's input, which in our case could be a 20 by 20 short, small image, and then scan the whole picture and extract those images, similar to what I just searched, into what we call them candidate search windows, to send them into the classifier to do that. Obviously, we were to do that though, and the size of the object that we're looking was much bigger than the size of the data that could be fed to the classifier, the candidate search window, we will have to be creative and do what we call an image pyramid, which means downscaling the image successively and iteratively until the final image matches the size of the detector. So that way, larger images, larger faces in this problem could also be shrunk to the size of the detector's input receptron, let's call it, so that it could be processed and analyzed by the neural network classifier. So to do that, and to take a nice example of what the detector sees, we take that big picture, then we shrink it successively and iteratively, and we generate we keep the window size stable because this is the size of the detector. So what the detector sees, it's a sequence of all these tiny images until we find out till we feed, I should say, the object that we're trying to find and feed it into those small windows. Now, this is a big problem because it translates to a huge number of data that needs to be sent either from the memory to the CPU or to the ASIC or to whatever other system that we're using to process the data. It increases with increasing the image size, and as the resolution of the sensors today increases to 4K, 5K, 8K, and so on, obviously this becomes a huge bottleneck. At the same time, this translates into many more windows, for example, in a 320 by 240 image, which is very small if we think about it, and a huge power to performance benefits. In other words, we spend much more power, much more processing and resources to simply make sure that we cover all cases to be classified by the detector versus actually seeing things. So this is a huge problem. However, humans, we have the ability to actually think and see in a different way than a single camera, and with the ability to put and mimic the mammalian visual system, such as having two eyes, or as we call it, stereoscopic system, then we can use this principle, and it's part of a sensing. So I'm not going to talk in the interest of time on how this is achieved. However, we can use what we call stereoscopic cameras or other sensors such as LiDAR technology and many more to capture depth images. This technology is available as part of the sensor, and we can use it to our advantage, because when we use it to our advantage, we can also use other human-based approaches or mammalian-based approaches, such as what causes us to turn around when we're seeing something that secures our attention, for example, even for a teeny bit of a second, that makes our eyes focus on a particular object. So if I'm outside in the field and I see something moving, human nature will immediately, at least for a fraction of a second, make my eyes go to that particular way, especially if that moving item has a context into how it affects me as a human person. So if I'm walking in the street and I see a truck coming towards me, obviously, when I see the truck, even if I'm doing something else, human silencing will focus on the truck to inform me that this truck is coming to hit me, so get out of the road, take action as fast as possible. At the same time, when we're looking in a large, let's say, view earlier, for example, we were looking at a nice view of the city of Seville in a previous conversation I had with a colleague. And you can see a lot of green in a forest, etc. However, that information may not be of immediate context to what I need to decide. So if I'm walking in the countryside and I'm looking at nature and the truck is coming to hit me, obviously I have to prioritize. And what's important to me, it's the truck that's near to me, closer to me, and much more ready to make an impact versus nature or a beautiful field and many, many other non-important things. So in our first approach, we started to say, okay, we don't need to search everywhere. Why don't we use, for example, motion to detect important changes? Why don't we use depth to estimate the size of the objects that we're trying to find out, given that depth gives us the relative distance of the particular object to the camera, and I will explain how that happens in a couple of slides further down the road, and remove unnecessary things that are of not too much detail, let's say, so that we can see only what we need to see and classify only that part as whether it's an object of interest or not. So let me start by saying what we can do if we only focus on the depth and on the edge. If we focus on the depth and we know the relative depth using any sensor that can give us the depth, then we can extract immediately the size of the window, both in terms of the physical size if we want to determine how big the object is, but most importantly, the size of the object in pixels. And if we know that, then we don't have to worry about outsizing, short sizing, or changing the size of the detector's windows to do the whole process that we talked about earlier. Instead, we can exactly state into our processing stream the size of the object of interest, and we can only fit those windows that match the size of the object of interest. At the same time, too much detail may be important, too little detail may not be important. So a very fast and very easy approach is to have an edge-based background removal. In the example I'm showing in the picture, for example, we can do a very quick scan and see where the edges are. And if we know that there are a lot of edges, it implies that maybe we take a more detailed look. But if there are not too many edges, maybe this is a lot of things that are in the background that are not important to us or immediate importance to us, so we can ignore them. And instead, focus on items that are very close to us. They have a lot of detail inside and are important to the computation, similar to that. So if we can use that, for example, if we're talking about an object that has a lot of edges, this can be determined empirically or based on the application that we're trying to address. We can discard regions in the picture that are of no interest. They have no details, and only focus on the regions that have particular details of interest or are good candidates to contain the object that we are seeking to see. Now, at the same time, I mentioned earlier about motion. If we don't have motion, maybe we don't need to spend too much time processing that particular scene. So if I'm watching Usain Bolt run the 100 meters race, I don't need to focus on what's happening behind or what's happening in front. I only know to focus on what's changing every unit time and focus on where I need to predict, essentially, maybe through some Kalman filter or some other motion detection or estimation approach, where I need to look again in order to detect the object in the future, and so on. So as a very nice and quick example, if we take all these very simple approaches and put them in a nice visual cascade, So starting by a stereo pair of images, so similar way to our eyes, we extract and find the areas of change through motion. Using the depth, we can compute the window size. Using the edge, we can remove and filter background regions and only focus on the areas that we need to shift our attention to and send it to the classifier for performance. And this is work that we have done in the last few years. If we use all these very simple techniques, guys, we can reduce by almost 99.4% the number of windows that are sent to the classifier for processing. And we implemented that on various scenes with a lot of motion, including the London Olympics 100-meter race, because we're talking about a race that has a lot of motion, just to see how this approach would work. And even in high motion, let's say, attention generating scenes, only 1% of the windows reach a classifier, and we need to focus on. We can easily distract the rest of the stuff. And if I go back here just to show you this translates into huge savings, both in power and performance down the road. So let's focus now, which is the third part of my talk. Instead of focusing on what to see, let's focus on how to speed up how we see things, which is the classifier itself. Obviously, we know that designing deep neural networks, it's very challenging due to memory and so on. So what happens right now is we try to design and train a good model, convolutional or deep neural network, for example, get some results in terms of the accuracy and the performance, and then start to optimize it by maybe reducing some values, by changing some parameters. I'm going to talk about this in the next couple of slides, to feed it on our embedded processing platform and so on. What is the current state of the art? Current state of the art includes a lot of small neural networks, such as YOLO and so on, that focus on looking at the whole image as a complete picture. And YOLO translates to you only look once, very similar to you only live once, much of YOLO. And YOLO has been actually the state of the art for the last few years. The guys that developed YOLO are doing a fantastic job. The problem is, though, once you put it on a very resource-constrained device, then you need to play around with its parameters, try to optimize, try to do many more things to make it fit. And depending on the application, you might have to outperform, to trade off some performance for accuracy and vice versa. Another approach is what we call region proposals. Basically, they try to extract objects of interest or bounding boxes, as we call them, to say that in here there should be an object, such as RCNN, fast RCNN, and faster RCNN, some very well-known networks. These are typically more accurate, but they're slower and require multiple passes of numerous reasons and so on. So what usually happens is we try to design a good model, not thinking in terms of the resources that we have. Instead, we try to do a good model and then optimize it using some methods to reduce what this model needs. And then eventually, once we do that, then we can maybe update it over there and so on. So again, this is what happens right now. Now, how can we do that? Well, we can use techniques that are widely available now, and there's a lot of research in improving these techniques, either structure or unstructured pruning, which means removing one neuron or two neurons and so on, strategically or holistically or empirically or heuristically, and determining what is the impact on my model's accuracy, what is the impact on the performance, and so on. Then replacing that neuron with another one, maybe share some weights to reduce the overall memory size, or play around with the bits to reduce the overall bit size and so on, which is called quantization. So, for example, if my model that has been trained in a high-end training tool such as Keras or TensorFlow using Python or MATLAB, maybe the weights are 64 bits, but if I put them on a chip, on a processor, for example, that runs 8 bits, then I need to quantize them in 8 bits. so that they can be processed by the multiply accumulators circuit that processes only 8 bits, for example, and so on. Here we can do some optimizations at the hardware level. For example, we can change the arithmetic computation that we're doing for either fixed point or limited fixed point, but we can also optimize or improvise and think outside the box and change the structure of computation, such as doing systolic arrays and so on. In fact, there's a very well-known term, post-von Neumann computing, which comes to usually characterizes AI circuits nowadays, where we deviate from the traditional fetch, decode, execute approaches, and we accelerate these systems through novel structures such as systolic arrays and so on. However, all these are computational. They're limited by the available technology. They're limited by the physical resources that we can put and so on. Through the second case study that I want to show you how we can think again a little bit outside the box, think how humans could see, and possibly integrate some mechanisms that can selectively choose where we need to focus, where we need to process, in an effort to generate much smaller models, much smaller requirements, if I can use the word, and feed it without any loss of accuracy or loss of performance into our edge devices, let that be an ASIC, an FPGA, a microcontroller, and so on. And the case study, it's the UAV vision. See, this is something that we have working with my team here for a while. UAVs are starting to be used pretty much in a lot of applications, such as monitoring, emergency response, and so on. And they are extremely challenging because they are usually equipped with extremely high-resolution sensors like 4K or 8K cameras. They fly in very high altitudes, and traditionally, when we're looking at computer vision problems, we're looking at them from the perspective of a human person. So our camera was basically put vertically in a tripod, an attachment, or whatever, and made to stream visual information in a similar way that mammals do. However, if we're looking at UAVs, then we go into what we call bird's eye view and top view, and things that maybe we need to start shifting a little bit the way we see things and the way we analyze these things. So using larger networks may not be a good idea. Reducing the image size, which traditionally has helped, also may not be a good idea, especially when we're talking about top view images. And the reason that we do that is during the training stage, if we train our system in images that have been captured from the top view, and then we reduce the resolution or change and do an image pyramid, we lose a lot of visual information, features that have been used in the training. And as a result, we're going to lose accuracy and performance. So what is the design question that we tried to address when we first started looking at this thing back in 2017 and 2018? What is a suitable convolutional neural network architecture that can be used to identify objects from on board the AAV? Well, we started by taking well-known neural networks, modeling them, training them, putting them on high-end training engines such as NVIDIA and Google TPUs, and construct through our data set the model. Then once we construct the model, perform design space exploration and find the model with the best performance, accuracy, trade-off, and so on. So our very first approach, which was geared towards a low-end embedded processor that ran Linux back in 1918, was achieved on a PC-based CPU platform, and also on an Autoread board. I will show it in a couple of slides. And basically what we did is we did a design space exploration by starting from a fundamental neural network, by going into 512 by 512 images and essentially adjusting the resolutions and progressively reducing the feature maps, the feature sizes by a factor of 2 until we get results. And the very first approach was very promising in the sense that when we compare it to unoptimized versions, we actually had a very good performance to accuracy ratio, to resource overheads ratio, both power and memory, compared to if we just took existing neural networks. So what is the $1 million question though? Can we do better? For example, if we resize the input image size, then we lose performance, we lose information, we lose accuracy when I say performance in terms of the performance. So what is the detector input size? If we get the input image that is shown on the left, and the input size is a 512, let's say by 512, we have two choices. Either we uniformly reduce the input size and resize it, which is the bottom part, or we crop and feed only part of the image to the input of the detector. None of these approaches are bad, but none of these approaches are what a human or a mammal, let's say, or any intelligent, let's call it, creature would do. So if we do that, then we can detect some things. We can have some detections. For example, in a test that we did with 5 pedestrians, we were able to detect the 2, but it was not obviously the ideal scenario. What if our problem is trying to model traffics? And by traffic, I mean vehicle traffic, vehicular traffic, especially in large cities where traffic becomes a major issue. And of course, it impacts both the citizens' well-being and also the business and everything else that needs to travel from point A to point B and so on. Obviously, if a UAV is flying at a very high altitude, then you're limited as to the resolution and the detail that you can see. So reducing the resolution is not a good idea. If you are flying at a lower altitude, so you can have high resolution and good detail, so you can reduce the input image resolution though, then your flight time is significantly reduced because you cannot see that much space. So you have to fly a longer distance, a larger coverage area, if you can say that. So it probably impacts the application itself by limiting the useful time that the UAV will do all these things. So what would biology do? Can we get inspired by biology? Let's see. If a human person were able to see that, obviously by looking at the whole picture, our eyes would focus on the specific parts of the picture that are of relevance and importance to us. And this is usually what the human saliency does. So if we can design an attention mechanism, which could be, for example, motion or any other idea, then we can say, you know what, maybe I need to look in that particular part only for now. If we do that, then we can see that we can detect all those pedestrians. Obviously, that's because all these pedestrians were located in the center of the picture and close to each other. In the scenario where another pedestrian will come either from the left or to the right of the picture, then obviously this could have resulted in okay results, or maybe we could have missed it, or maybe it would have been just an extra delay by the time we detected the motion and shift our attention to the left or to the right of the picture. To solve that, how about we think how a human would be? What happened in the previous frame? So I had motion over there. I saw something coming far away. Maybe now it's time to shift back and look at that particular area. Did that person come close? Did that object come nearby? Can I, or does it impact my context? So if we do that, then we can limit what the neural network detector needs to see and use any method, such as, for example, optimization or model, to detect in real time these particular objects. So by using the method that we propose, as we call it tiling, then we do not compress, enlarge, or shrink any information. We do not distort the image. We maintain the object resolution, and we just, depending on the tiling factor, let's say 2, 4, 6, or whatever, we only choose which tiles will be processed by the small neural network every, let's call it, cycle. So if I'm at a parking lot and I want to process this, obviously the size of the processing tile it's directly related to the input of the neural network size. So if my input is, say, 2 times the CNN size, then, or a little bit less than 2 times, then what I'm going to generate is I'm going to generate tile with the yellow outline and the tile with the blue outline. So we have 2 tiles. But as you see, both of them, even though they do contain overlapping information, are not distorted, and all the visual information is right there as it's seen, captured, let's say, from the sensor. So by selectively processing, though, the tiles that are of higher importance, of higher interest to us, then we can only process the necessary amounts of data and are able to use small, flexible neural networks that do that. And if we integrate with a memory mechanism that remembers, for example, where we have detected something in the past, then we can very easily, a memory buffer, for example, or a memory counter, then we can detect, oh, what did I see earlier? For example, a vehicle, a pedestrian. What was my confidence? Was it good? So am I 100% sure I saw a pedestrian there? So maybe in the next frame or so, and if we're talking about a pedestrian, the pedestrian would not move by a very fast, by a very large distance. Ideally, if the pedestrian was not in a car, let's say, otherwise it wouldn't have been called pedestrian, obviously. And as a result, we can use these metrics to decide when we should shift our attention to the next, change and so on. So the memory mechanism is good because we can use very simple methods like intersection over union or union over intersection and so on. Intersection over union, if it's a high, implies high correlation with the previously stored box. So if I have 2 objects nearby in successive frames, there's a high probability that the same object is the one that's being detected. But if we have a low intersection over union, it implies that maybe another object is nearby. So I have to shift my attention to both tiles, process both tiles, and do a better detection. Now, this allows us to maintain a very small buffer, maybe 3 frames in our case, or 4 frames, or depending on the objects, if the objects do not move, for example, if I'm looking at cars in a parking lot, the probability of a car moving, it's very little, it's very small. So we can only focus on the objects that move fast and so on. So if we can do that either by doing all tiles or by a non-intelligent necessary way by doing a round robin. So one frame I'm looking at one tile of a frame, the next frame the other, and so on. If I integrate some minor intelligence such as what did I decide, what did I find out in the past, and if I can use a memory of what I found in the past, then we can definitely run all this along with a standard model such as a tiny YOLO. And this is the part where I mentioned earlier about putting this on a very small embedded board directly attached to the UAV. And I can see that even if my very first network that was optimized only for this particular application and was very good in terms of the performance, as you can see, it's 0.2 seconds versus 1.6, but you can see that its accuracy was ridiculously lower to the tiny YOLO. However, I can make my accuracy up to 91%, which is extremely good, and only sacrifice maybe some milliseconds, 0.207 to 0.394, as you can see from the experiments here. So this just shows us that if we think a little bit outside the box and consider how a human person, how an intelligent being would do that, that would enable us to actually do that. And this is a very small demo of a version of the detector, the car detector that we run, running in an intersection in the city, showing that it almost detects virtually all the moving cars, maybe 1 or 2 misses, and so on. So what is their impact? Through the tiling, we improve the sensitivity, and by intelligently selecting these tiles, we can minimize maximize the performance and minimize the data accesses from the memories and so on. It's agnostic of the CNN, so that enables us to go into the CNN or the ANN parameters, fine-tune it, and get even better performance. There's a lot of room for improvement, and this is a framework that we worked on by focusing on optimizing tiny small networks using the pool of networks, which is shown into this part of my diagram, and instead have one, let's say, initial good version of our network, high-level version of our network with high resolution, etc., to get the initial positions into the picture of the network. And by using these mechanisms, then we can, depending on what we detected in the previous frames and so on, identify through a pool of convolutional neural network models that can be stored, since they're very small, onto the device, through a selection process, which ones are better geared towards a specific object at the specific time, or the specific height, distance from the camera, that is, and so on. So by using one initial network, we can detect the initial positions. Then we can do these tiny small neural networks through a pool of selector of these networks, and then process depending on the object of interest, depending on where the object of interest has been found in the past, and so on. And in order for us to make sure that we keep track of what has happening, we integrated a very simple tracker. The Lucas Canada tracker, it's not really of importance to the particular talk. I will explain later why. And then through that, then we're able to go back into the beginning if there is a need to cross-validate and make sure that nothing new came into the picture. Now, the initial position estimation is very important. If we can see that the position of the person of the object of interest is in a particular coordinate, let's call it, in the picture, then the base CNN classifier, which is based on the larger model and the larger in terms of performance and the more latency in terms of the performance, but more accuracy in terms of the detector neural network. And then with the tracker, which is a very small and very simple tracker, this is why we used it. In fact, this has been published back in 1981, so it's a very well-known tracker since the last 30 years. Through the tracker, we are able to correct, and then if something else has come into the picture, we're able to detect it and not miss any of this. This enables us, even if we run it on a Raspberry Pi 3, for example, or an Android board, or any small CPU such as a tablet or a laptop, the normalized power consumption, as you can see, this whole framework achieves super significant power savings, and of course maintains really good accuracy, as you can see by some demo videos that I'm running out here. All of the pedestrians here, you can see, are being detected, and I'm only focusing on those tiles that are bound by the white squares, as you see on the picture. An even more impressive demo, it's our vehicle tracking detector that runs on the drone using an NVIDIA Jetson as a payload. And if I push the button, you can see here, I'm hopeful that all of you can see it, the detector, the blue rectangles detect the cars where they're going. And as a result, we are able to extract, for example, vehicle traffic trajectories and so on. Now, what we have observed is that each application has its own requirements. Some applications may not need deep neural networks. Deep neural networks is a nice buzzword. A lot of people do deep neural networks. But if you're trying to put it on a tiny device, on a tiny CPU, or a tiny FPGA, or a tiny circuit, sometimes the application may not need a deep neural network. Think outside the box. Sometimes, especially we're talking about vision applications, unfortunately, to get performance, we may rely on deep neural networks. In that case, we can figure out, again, what is the performance requirements and metrics for each application. And by using that as a directive, and by also thinking as humans or intelligent beings would think, let's get inspired by biology. Let's think outside the box. Let's think outside the circuit itself only. And let's see, okay, if I can optimize my circuit up to a certain point, what else can I do to be able to fit the system there? This will enable us to shift this in the future, have, for example, vision-based swarms, IoT devices swarms, which would be able to provide all these by collaborating with each other and have collaborative vision algorithms. And as a conclusion, to design deep convolutional circuits and architectures, we should not only look at design exploration only on the device itself. We need to focus on all the layers. We need to do in circuit application and so on. We need to focus on the applications requirements, and we also need to take into consideration the technology, the device limitations, the model, the tools, the modeling, for example, tools that exist, the reliability, robustness of the systems. At the algorithmic level, we need to, for example, security and robustness are very important parameters, but it's a whole holistic approach that you need to look at all layers in order to go down to the device and build and design the better, the most efficient, the best power to performance essentially device. And last but not least, in terms of AI applications and AI devices, we also need to ensure that we have tested it in the field, no matter where we're going to do it, because it's an approximate computing device. Its operation, including the hardware's operation. For example, if I send a drone to monitor an electromagnetic around an electricity producing station, for example, and there is a lot of electromagnetic radiation, my circuit may be vulnerable to errors, and as a result, I might need to strengthen the circuit, maybe do radiation hazard strengthening, and many, many more other optimizations. So I need to look at it again in the field to ensure that what I'm doing is correctly validated, and as a result, I'm able to extract what I really need and satisfy, if I can use the word, the performance, the requirements, and so on. So at this point, I would like to acknowledge, of course, my colleagues at GIOS, my former student, George Plastiras, and of course, my colleague, Christos Kirkou, and some of the colleagues, for example, Shafiq from NYU Abu Dhabi and Christos Vouganis from Imperial College London, whom we have collaborated in the last few years towards these works that I have just presented. And of course, now it's time, if there are any questions similar to the questions inspired by Isaac Asimov's iRobot movie adaptation, what are the right questions, detective, and I'm at your disposal for any clarifications you may need.
Okay, many thanks to you from the very nice talk. We actually have one question here in the chat. So, a question by Altamiro Suzin. A very nice presentation, thanks. Some edge vision needs a high resolution. For others, low resolution is sufficient. Do you see how we can divide applications based on this approach?
That is an excellent question and a very nice observation. Yes, there is a huge amount of work done now in finding where I need low resolution, why should I need, for example, high resolution, and so on. There are a lot of techniques, both at the model level and at the hardware, software co-design levels. Adaptive resolution, sometimes you might want to adapt your neural network to various resolutions during the computation stage. In fact, reconfigurable hardware are actually being targeted as a possible platform for these things. So yes, that's why I mentioned that if you look at the application demands, the application will give you a very nice overview of what requirements you may need, and a lot of optimization opportunities, not only on the resolution, but beyond the resolution as well.
Okay, thanks. As we wait for more questions, I have a question also. Yep. So you have detailed several algorithm-based solutions to reduce the complexity of neural networks for the edge. How do you see the hardware optimizations? For example, you can refer to this drone case. What do you have there on the hardware acceleration, and how do you program the hardware, and what optimizations are made to make it very energy efficient and power efficient and so on?
That's a very good question also, Claudio. Basically, at the hardware level, there are, of course, the standard optimizations you can do. For example, you can do dynamic frequency scaling, etc. If I have to, take it to the circuit level. However, no matter how many optimizations we can do at the circuit level, we're also limited by what technology offers us. At the same time, we're limited by the budget, we're limited by the constraint of the physical chip. So if I have to put a systolic array, which is a nice interconnection, let's say, hardware structure that is more suitable for neural networks operations, systolic arrays, for example, GPUs and tensor processing units, they're based on this fundamental reorganization of the computation, etc. If we're talking about monolithic chips, then there is a limited number of optimizations that we can do at the hardware level, because I can only put that many wires, I can only put that many connections, I can only put that many transistors. If we're not talking, hopefully in the near future, about in-memory on top of hardware, of top of devices, processors for essential integration, and these are some techniques that are being very well looked into by various groups across the globe. For example, Onur Mutlu in ETH Zurich and Kaushik Roy, to name a couple. These people are working into how this on-memory or near-memory computing, which is geared by the ability of the hardware to give us, for example, stacked integration, memory with the processors. So any emerging technology or neuromorphic computing, memory stores, for example, will be extremely helpful for us in the future to run these algorithms. For example, spiking neural networks are extremely good for neuromorphic computing. And as a result, I see that as we enter, as the technologies are becoming more mainstream, even quantum computing has been mentioned in the past, as these hardware technologies become more mainstream, then we also need to, as I mentioned in my last slide, we need to look at it at the cross-layer level. So how can we take advantage of the abilities of in-memory computing in a 3D chip, for example? How can we take advantage of quantum or neuromorphic computing in the algorithm as well? So this could expand a whole lot of opportunities in the future. Right now, with what we have, unfortunately, our options are quite limited. Of course, depending on the application. So if we're looking at an application where it is necessary to do that, which justify the high cost of an ASIC, then obviously we can, put more hardware, work it a little bit around the design parameters that we have, and so on.
Okay, nice. That's nice to hear that the 3D integration will help, and this post von Neumann models are going to help also for computer vision at the edge. There's another question here from Altamir Suzin. Do you think non-uniform resolution sensors, higher on focus and lower at the boards, would be useful to increase performance?
Yes. Another very good question. Yes, there is a lot of work done by the sensing community and the sensing industry to develop, for example, event trigger sensors. So the sensor only activates and focuses only on a particular event. I'm not 100% familiar with how the technology and the result of that sensor is. However, event-based sensors or other types of sensors, yes, there is a lot of work in the sensing community that are going to eventually give us these ideas, give us these opportunities to increase the performance in the future. For example, 20 years ago, we could not use LiDAR. LiDAR has been very expensive. The last few years, slowly it's becoming cheaper and cheaper. And LiDAR, along with RGB images, has given us the ability to do 3D image processing as well. which helped with the example I showed about the window size, for example.
Okay, nice, thanks. There's another question by Altamiro Suzin. Can we say that vision is not a matter of pixels, but regions, edges, and structures? Could
Yes.
a language to describe images at high level help vision process?
I don't know if Altamiro was in the beginning, but what I was trying to essentially point out in the beginning is that pixels, it's what the sensors gives us. Vision is how do we make that information into useful, contextual aware information. So regions, structures, features, objects, how they relate to the context, it's what vision is about. The pixels themselves is just data. For example, if I put on, just to give you a nice example on how I relate it, if I wear glasses to improve my vision, I'm not improving my vision, I'm improving my lenses, my eyesight. It does not improve my vision. My visual cortex remains unaffected.
Yes.
But if I can not see above a certain length due to me being nearsighted, for example, if I wear lenses, then it will bring me that information to my eyesight, let's say, and transfer it to the brain. But what the brain does with the new and improved eyesight, it's part of what computer vision is all about.
Okay, nice. So let's see if we have so we don't have more questions. So I'd like to thank you very much again for the very nice talk and for accepting our invitation. And don't know if you want to say some words. So
I also, as I said earlier, I'm very honored and very happy to share all this work that we did in the last few years with you. And I look forward to, if anybody has any questions, you can always reach out to us. You do a Google search, you will find out where we are. And I'll be happy to answer any emails later on to that. And of course, please continue, Claudio and the CASS team over there. Please continue this sequence of lectures. Both my students and myself have watched previous recordings and they are very helpful to us.
Okay, thank you very much. And so let's thank again Professor Theo from the very nice talk.